The last time I gave the talk, I talked about a zombie planet around Fomalhaut, and this time we're going to be talking about a whole bunch of dead stars and the sort of leftover debris that might be in orbit around them. So when we talk about planets these days, planets are everywhere. It used to be whenever someone had an idea that some observable signature was due to planets, people would kind of laugh at them because, oh, there haven't been that many planets found. We don't know where planets exist, that kind of thing. But now we're in an era where we have thousands of exoplanets that have been discovered. And this is a plot from exoplanets.org just the other day, where I took all the observed planets, both from radial velocity surveys, Kepler, direct imaging, and I plotted them up in sort of a weird way. I plotted them as a function of the effective temperature of the star that they were orbiting around, their mass. The symbol size gives you the mass of the star, and the color bar gives you how big the star is. So most of the planets we have seen are around sun-like temperature stars. They have a large range now in planet mass, thanks to things like Kepler and very precise radial velocity surveys. But we're also starting to probe stars of very different radii as well. And what that's telling us is that we're seeing planets in orbit around stars of many different kinds of evolutionary states, from somewhat young stars all the way up to giant stars, which are sort of sun-like stars that are going through their end phases of life. And so when I was a wee grad student back in the early 2000s, my advisor talked to me and he said, you know, you should take a look and see what happens to a planetary system when its star dies. And that was my fall project in my second year of grad school, and it became eventually my most cited paper on dead planetary systems. So we'll talk a little bit about that. So the end point for most stars is the white dwarf. White dwarfs are also known as degenerate stars, degenerates, right? So not 2016 presidential candidates, but what's happening here is basically the star, as it's burning its hydrogen, fusing it into helium, it's creating this core of fusion ash at the center of the star. And over time, it exhausts all of its hydrogen, and it puffs up to a giant, and eventually starts burning helium into carbon and other things. And eventually that runs out, and it puffs again into a bigger giant, and eventually loses most of its mass, about half if we're talking about a solar-type star. And so you're left with this sort of corpse of a star called a white dwarf, which is basically just the degenerate core of that star. And it's so dense that the electrons are sort of bouncing together, and they're providing the pressure support against the gravity of the mass. So a typical white dwarf is about 6/10 of a solar mass, and its radius is similar to that of the Earth. So these are very dense objects. They're the endpoint to stellar evolution for any kind of star that's not going to explode. And for the longest time, people thought that this process, losing more than half of its mass during this evolution from being a normal star to a giant, eventually to a white dwarf, meant that any planetary system that must be around it must be destroyed instantly from this process. If you do sort of a simple gravitational calculation, you think, okay, if I suddenly remove half the mass from a star, all your planets just go flying out, right? Because they suddenly have way too much energy for the gravity of the star. But it turns out that's not what's happening. And then I'll just point out, and I'll get to more of that story later, but I'll just point out, if you just take a census of the nearest 10 parsecs, or 32 light years, we have, sort of estimates for the numbers of different exoplanets and M dwarfs, brown dwarfs, all the way up to A stars. And unfortunately, they didn't include white dwarfs, my favorite star, but white dwarfs are about as numerous in local space as sun-like stars. So you just want to keep that in the back of your head, and I'll get back to that by the end of our talk. Okay, so we can do a thought experiment about what happens to planetary systems by thinking about our own solar system. Now, we're definitely in an age where we shouldn't only be thinking of our solar system as a prototypical or archetypal planetary system, but the solar system is always a good place to start, right? We shouldn't be limited by what our solar system tells us, but it's always a good place to do thought experiments and stuff like that. So if we have a little picture of the sort of inner solar system, including Jupiter and Saturn, our asteroid belt, and then all the terrestrial planets. We're sitting here 4.5 billion years. Don't argue with me about that. And we're in a nice, stable, kind of happy place. Nothing's going to happen for a while. I do have to say, unfortunately, in a billion years, we're hosed. That's when the sun, due to its fusion, keeps getting a little bit hotter, and we'll have runaway greenhouse gas effect. Global warming on a much more severe scale. Okay, so that's about maybe there. And then eventually, we're going to be in the red giant phase, right? Our sun's going to puff up. I also have bad news. If the heat doesn't get us, the stellar surface will, because it's going to puff up to greater than an AU. And a couple things are happening, right? It's so big, it has tides, really strong tides. So anything close to the star gets eaten. And once it goes in the stellar envelope, we think that's pretty much the end. But Mars seems to survive this process, maybe. And part of the asteroid belt might survive, and I'll go more into that later. And Jupiter's all the way out here. Now, by this point, the sun actually hasn't lost a whole lot of mass, maybe 1/10 or 2/10 of a solar mass. So you'll notice, if we go back, if I can figure out, yeah, hey, that worked. Where's Jupiter? Is it in the same place? No, it's getting a little bigger. It's further out. So what's happening here is the star is losing mass, but it's losing mass pretty slowly, so that the orbit is not perturbed very greatly. We call this an adiabatic process. This is like boiling the frog. You put the frog in the pot, you slowly turn up the heat, frog's fine. Slowly turn up the heat a little more, frog's still fine. Then you keep going until suddenly the frog's dead, right? So we're basically boiling the frog with Jupiter here. It doesn't really care that the sun is losing mass. Its orbit, to conserve angular momentum, just slowly expands a little bit. And it expands by a predictable amount. So if the sun has lost is 80% of its mass, Jupiter has moved to an orbital separation that's 1/80%, right? A little over 1 point whatever. I can't do math in front of people. Anyway, eventually, the star loses mass a bit more quickly, and we're left with the remnant white dwarf. But it still has not lost mass too quickly for the orbits not to react to it. And the other thing that I want you to remember is that now we have, instead of a solar mass, we have like a half or a 6/10 of a solar mass object at the center of this planetary system that, for all intents and purposes, I'm going to claim to you survives, and then I will prove it to you in some way later. But basically, everything now is much more powerful, right? So in dynamics, we often care about the mass ratio between a planet and its central object. Okay, so when Jupiter tugs on anything, we think about how much that happens by the ratio of Jupiter's mass to the central mass. So now, the central mass has gotten smaller. Jupiter is already kind of a beefy fella. He's now even more beefy with gravity because he's more of an influential player in this gravitational system. That will become important later, but again, not right now. Okay, so now a little detour. So 5 years after Einstein predicted gravitational waves, Van Manen was at the Mount Wilson Observatory, and he found a curious faint star. And he noted, when he took the spectrum, this is by far the faintest F-type star known at the present time. So what he had actually seen was not an F-star. This is a modern spectrum of Van Manen's star. It still carries his name to this day. But it was very unusual because he was able to measure the parallax to this star and found that it was very close to Earth. So given that it was faint in visual magnitudes and close by and moving very fast on the sky, you could tell that it was a very intrinsically faint star, not just visually faint. So this was the first-ish discovery of a white dwarf. And on top of it, it wasn't even a typical white dwarf. It looked like an F-star because it had these metal lines present. You know, if you look at solar-type stars, they have lots of metal lines from different atomic elements. And here we have calcium. These very strong lines are calcium, in fact, the H and K lines. So it looked weird, and it was faint. And within a few years, people realized that these were intrinsically faint stars, about a 10,000th the luminosity of the sun, and that these must be unusual stars, and they called them white dwarfs. And now we know what they are. They are the dead corpses of stars. But they didn't know that then. And they didn't know why there were metal lines. And it turns out you wouldn't expect to see metal lines in most white dwarfs. And that's because they're very dense. So what happens with a white dwarf is you have this core of carbon and oxygen, and then you have a very thin layer of either hydrogen or helium, very low density gas. And if you have any kind of metals in this very thin atmosphere, they get pulled to the center of the star, out of sight. So in a very short time, much shorter than the time we would be able to actually observe these things, these metals, whatever remnant metals might be present in the atmosphere, would disappear. So you would only expect to see pure hydrogen or pure helium white dwarfs, or if you had no thin layer of hydrogen or helium, or there was some sort of convective process, you might also get carbon. But those were the only three elements you might expect to see. So it's actually a puzzle why you might have metals in these atmospheres. So for the longest time, people thought the metals came from the interstellar medium. You know, the interstellar medium, the stuff between the stars, is not empty. There's dust and gas and other things. So as you have a white dwarf plowing through space, it will pick up some of this material. So they said, that must be why you see metals. They're just picking up dust from the interstellar medium. 1919. The 50s, 60s, and 70s was when people came up with the idea that the interstellar medium was accreting stuff. And then 1987 happened. And something unusual was found. So two men, Eric Becklin and Ben Zuckerman at UCLA, were doing an interesting study. They were looking for brown dwarfs. And in 1987, no one had seen a brown dwarf before. And they thought, quite rightly, that it would be easy to find brown dwarfs in orbit around white dwarfs, because white dwarfs are intrinsically faint, and so faint brown dwarfs are easy to find, especially if you look in the near infrared at sort of the same wavelengths that Frank was putting up for that galaxy cluster. So what they did is they were looking at a whole bunch of white dwarfs looking for brown dwarfs. And they made a discovery. They said, we found a brown dwarf, yay! And so they, if you took a measurement of the brightness of the white dwarf at different wavelengths, so this is flux, in wavelength. As you get to longer wavelengths, this is the white dwarf. Its flux goes down. And when you actually observe this particular pulsating white dwarf, G29-38, it does not go down, as you would expect. It gets brighter. This is unusual. So what's happening is that there's an extra cool source of light in the system that's unresolved. And this is called a spectral energy distribution. So when Becklin and Zuckerman first did it, they only had a couple of photometric points. And they said, we think we have a brown dwarf, but it could be dust, could be some other things. Well, it turns out this is dust. There's dust in orbit around white dwarfs. So that's already weird. And it kind of, there was this great paper in 1990, just a few years after this was discovered. Some people thought this was a black hole. Some people thought this was a pulsating neutron star. They had no idea. It was weird. But they decided, in the end, the best explanation was that it was probably dust, right? It was too bright to be a brown dwarf in the end, and brown dwarfs were eventually discovered. Now, you can sort of make a model of the dust disk that must be around it. And you can just assume a very thin, flat disk that's passively re-radiating the light from the white dwarf. And when you do that, you infer that this dust is between 10 white dwarf radii and 30 white dwarf radii. Now, if you remember, a white dwarf radius is about the same radius as the Earth. So that's not very big. And this is a massive 0.6 of a solar mass star. So the orbital velocity here is several hundred kilometers per second. We're starting to get to an appreciable fraction of the speed of light at these velocities. So you have dust nearly at the edge of a white dwarf's surface, whipping around. Okay, how do you get dust? Well, you get dust from planetesimals, maybe? That's what James Graham postulated. Okay, and there it stood for 10, 12 years, and not much else was done. It was an oddity. It was just one. So nature's weird. It always makes weird things. You can explain one thing very easily and then forget about it. And mainly we forgot about it because there wasn't a lot of mid-infrared observing going on. 5 to 10 microns is very hard to do from the ground. And so there it stayed until Spitzer was launched. And then suddenly we had the whole sky in the infrared to look at with very fine detail and with very fine sensitivity. And that's when a whole bunch more of these dusty white dwarfs were discovered. Furthermore, they were discovered not only to have dust, but when you took a spectrum of the white dwarf, you would see metal lines in its atmosphere. And if you thought Van Manen's star was weird, these white dwarfs were even weirder because a lot of them had only pure hydrogen atmospheres. And they were warm, pretty hot white dwarfs. So the settling time, if you dropped a bunch of metals into the atmosphere, the metals would completely disappear within a couple of days. So the fact that you even see metal lines in these white dwarfs meant that they were accreting an appreciable amount of material constantly, not just over 1 billion years or something, but that minute. Okay, so keep that in your mind with the other things. I think I've got more than 6 things in your mind, so you've probably forgotten half of them, but that's okay. I will remind you. In any case, if we go back to the structure idea, we can think about maybe a little bit more about what might be causing these strange dust rings and why this might have a connection to planetary systems. So if you have your white dwarf and you assume that you don't get dust closer than where dust turns into gas, seems like a reasonable assumption, and you say, okay, how far out do they extend? They tend to extend not too far out and certainly well within what is known as the tidal disruption radius of the white dwarf. So if we put a planet or anything very large here, it gets shredded apart and turned into little bits. And so basically, the dust lives within a zone where anything that might stray in that zone would get torn up to little bits. You can have different flavors of your model because this explains more technical details like why you see maybe additional emission lines like this. This is due to silicates. This is how we know it's really dust and not something else, because there's a very strong silicate emission feature. It's a smoking gun for dust, and rocky dust, not anything weird. And now, in the era of Spitzer and then the WISE survey, we have dozens now of dust rings around white dwarfs, and all the dust rings are about within a solar radius, or a little bit larger than Saturn's rings. So there's rocks shredding up somehow and draining onto their white dwarf surfaces, leaving telltale fingerprints of the material that they are made of. So already, that is super cool. This is why I stayed in astronomy, because my second-year project told me about crazy stars that should have nothing around them, having really cool things around them, shredding up and doing weird things. So that's it. I was hooked. And so over the next 10, 15 years, we tried to come up with explanations for why this might be happening and learn more about what this dust actually was. So we took spectra of white dwarfs, we looked at the white dwarfs in the infrared, we tried to gain populations to understand what was going on, et cetera, et cetera. And we came up with complicated theories for how the disks evolve with time. This is more for the scientists, but basically we think there's dust. The dust goes beyond the sublimation, it turns into gas. It accretes onto the white dwarf, that's why you get the metals. Some of the gas goes out back, so you have sort of a mixture of gas and dust. Maybe you can see this gas. And in fact, you can. So while people were taking spectra of white dwarfs to look for the metal lines, they also discovered, hey, there's these weird emission lines at 8,500. This is, again, calcium, but now in emission. So if you have calcium in emission, that means you've got gas that's glowing, hotter than the star at these wavelengths. And in fact, it wasn't just glowing, it was glowing with this very pronounced double-peaked structure. This is like a smoking gun for an accretion disk, right? Because you have different parts of that disk moving at different velocities, which creates your double sort of peak shape there. As you take all these little bits of velocities and spread them out in velocity space or wavelength space, same thing. So we have gas, we have dust and gas going on to the white dwarfs. We have things shredding up somehow. We even have like pictures of the gas. This is so cool. This is just in the last couple of months. There's a technique where if you take lots and lots of spectra and build it all up and decompose everything into velocity space over time with the assumption that you've got some sort of regular periodic event occurring, you can do what's called Doppler tomography. You basically pull out an image from the information, the velocity information. So what we're seeing here is an inside-out picture. So it's not intuitive. So you're not seeing exactly a ring like this going from the center to the outer area. It's more the other way around. This is getting toward the center of the star, and this is getting further away. But in any case, you've got this very interesting elliptical precessing ring of gas around a white dwarf that, with lots and lots of spectra, you can synthesize into sort of an image of what's going on with the gas. And sure enough, just like the double peak structure told us there was some kind of a disk, the reconstruction of the velocities show that there is a disk, but not only that there's a disk, but it's precessing around. This elliptical shape is precessing around and changing the shape of the spectral features that we see. So this is cool. I don't even understand this yet. I need to think about this more. But it's a really interesting way to sort of get a picture of the system that we will never be able to actually resolve with a telescope in any easy time. Now, I've taken some spectra as well. And in addition to gas in emission, we've even seen gas in absorption around these white dwarfs. So if you look at sort of the spectrum, again, around the calcium H and K lines, you have the main photospheric line, but then you have this little blip, just blue words, right? Now, the other thing about white dwarfs, because they're so dense, they have a strong pull of gravity, much like those galaxy clusters, much like the universe redshifts things. White dwarfs locally redshift light. So what happens is the light coming from the white dwarf surface is redder than it would normally be. So its photospheric metal lines are pulled away from the velocity of the white dwarf. So if you have a disk, you've got the gas not reddened quite so much. And it's like a curtain being pulled away. So the white dwarf's gravity pulls the curtain away and allows us to find these weak circumstellar gas features. You can actually do some calculations about, okay, given how wide the gas is in velocity, where might it be around the white dwarf? And sure enough, it's within 100 white dwarf radii or 1 solar radius. And that's roughly about where the sublimation radius of the dust is for this particular white dwarf. And so you can look at a lot of white dwarfs maybe and find similar things. This also says that this particular white dwarf, probably we're seeing the disk edge on right through. We're looking right through it. So that's kind of cool. So we've got these metal lines. If you have enough metal lines, you can actually build up the composition of the dust. The other thing that I should mention is that white dwarfs are extremely sensitive probes to accretion. A me-sized boulder falling onto a white dwarf every second is observable. That's not a lot of material. When astronomers talk about mass, they usually talk about solar masses. Well, these are like kilometer-sized asteroids falling onto the white dwarf every couple days or so, or every year. So it's not a lot of material. It's a suspiciously asteroidal amount of material. And when we look at the composition with these spectra, we find a suspiciously asteroidal composition, a rocky composition that is not unlike the bulk Earth composition or asteroidal compositions in our own solar system. So not only are white dwarfs weird because they have this dust that drains onto their surfaces, and we get to learn about interesting disk and accretion properties in sort of an extreme environment, we also, for free, get dust composition. And if we can link this dust to planets, we suddenly then have a way of sampling the terrestrial chemistry of dead planetary systems. So I'm going to argue now that these are asteroids. These are asteroids that have somehow strayed too close to their white dwarf. They've gotten shredded up. They've drained onto the white dwarf. And we can read their properties from the spectra of these white dwarf. This is incredibly powerful. We cannot go to other planets very easily, especially the rocky ones, and measure what the rocks are. We can do it with Mars. We send a couple robots. It's going to be a little hard to do it around Alpha Centauri or HD 209458. It's going to take a little while to get there. So this is one of our best ways of understanding the chemistry of terrestrial planet formation. This has implications for understanding how different or how typical our own Earth is relative to other stellar systems. And on top of that, there's only a couple of other techniques that get at the sort of chemistry of planet formation or the chemistry of planet atmospheres. So Nicole Lewis in a few months will tell you about how they do the chemistry of atmospheres. But this is sort of like the chemistry of rocks. So it's very exciting. I can't overstate that enough. Very cool. And this is being helped quite a bit by the ultraviolet instruments on Hubble. Because white dwarfs are typically more bright in the ultraviolet, and there are a ton of metal lines in the ultraviolet that are often not accessible in the optical. So instruments like STIS, which I'm in charge of and I'm legally obligated to promote, and also COS, both of them have been instrumental in measuring compositions, especially COS because it's very sensitive. Okay, so these things are also not static in time. We've seen examples of some of these dust disks changing on yearly timescales. We don't understand why. And we even see the emission lines changing with time, which maybe we understand. Some of them are maybe just precessing rings, and that's why they're changing with time. But these are kind of disappearing. So there's a quick evolution on a yearly timescale for some of these observable phenomena that we see. Okay, but now we've got this question, right? I just showed you how our solar system would survive post-main sequence evolution, or the death of the star. And it doesn't look too good for stuff that's 1 solar radius away, right? It gets obliterated. So nothing that started out that close is going to survive that close. The star is going to scrub all the material out to 1 or 2 AU because of its evolution. So we have asteroids living somewhere in these dead planetary systems, and they have to start out at a few to maybe 10 AU, and they have to go all the way down to 4.5 times 10 to the minus 3 AU. So remember, an AU is the distance from the Earth to the Sun. So they start out far, and they get really, really close. So how do we do it? This is something that me, as a dynamicist, or a pretend dynamicist, because I'm not a real dynamicist, I just play one as an astronomer. But this is hard to do. You get a little panicky. You get worried. How am I going to do this? This is my thesis. How am I going to finish it? Don't worry. Keep calm and focus on resonances. What are resonances? Okay, so you have Jupiter, right? It goes around in a certain amount of time. And in certain orbits, you have objects that go 2 times for every 1 time Jupiter goes around. They'd be inside if they did that. Or half a time as Jupiter went once. These are special orbits because at a given point in their orbit, they line up with Jupiter, they get a little extra tug. They get a little extra tug. And they get a little extra tug over and again until they have different orbits. And you can really mess things up this way. Gravity is weak, but it's persistent. Okay, so first, I claimed asteroids survive post-main sequence evolution, or the evolution of their star from middle age to the end of their life. But I didn't really prove it to you. So these are some simple calculations of the survival of fairly large asteroids from Pluto size, give or take, down to very tiny asteroids. And these are survival curves for different situations. So the sun will get to a maximum luminosity during its evolution of about 10,000 times the current luminosity, because it gets really, really big. And so anything that is smaller and closer than this line here will evaporate. Now, let's say you bump it up twice as much, then anything below this curve will survive. Now, we know from your pictures there might be a little bit of gas expelled during the late stages of death. And so that wind, while it doesn't mess anything up too terribly for big planets, can actually drag on small asteroids and pull them into the inner system where they evaporate. So if you're in these sort of regions, below these regions here, for given initial stellar masses, so if we talk about the sun, you have these two curves intersecting, and anything below and interior gets destroyed. But our asteroid belt extends from about here to here, and so there's plenty of big things that can survive these processes. And even if the big things here don't survive, these small things here move in and eventually survive if you get the timing right. So you can get anything that started out here to survive. And also you have to remember things are moving out in response to the mass loss of the star. So you can get a whole bunch of stuff that survives and a whole bunch of stuff from the outer system that moves in toward the resonances, if you're talking about interior resonances to Jupiter, which is what these are. You can also have exterior resonances. So if you have chains of planets, like the typical Kepler planetary system is actually like 5 or 6 super-Earths all mushed together in very tight orbits. So if you have chains of those kinds of planets, you can have lots of resonances, interior and exterior. Our own solar system has exterior resonances with the Kuiper belt objects. And there have been people, the list is here, who have measured or modeled the dynamics to see whether asteroids or comets in exterior resonances get kicked into the inner system. And what happens is the gravity of your chain of planets, or a couple of planets, basically kicks from one planet to the next until eventually they get kicked to the inner system. Now the problem is that most of the stuff that's far out is icy and will get evaporated much more quickly than the rocky stuff. So I actually favor that the stuff on the interior, even though it has a harder time of it during the star's evolution, because it's rocky, will survive better than the icy stuff far out. So I actually worked on an idea where I took the thought experiment of our solar system, and I just measured, and I put a whole bunch of asteroids, our own asteroids in our solar system with the known orbital elements, and I ran them through an n-body simulation where I made the sun evolve through its end of life, and then I just watched what happened between the asteroids and Jupiter. And what I found was that asteroids that were in the 2-to-1 mean motion resonance with Jupiter, an interior resonance with Jupiter, would get kicked in and tidally disrupt a few at a time at a rate of, a few per year or a few per tens of hundreds of years, depending on how long it had been running. And you can compare these models with the observed accretion rate of a population of white dwarfs to see if the model makes sense. So what do I have here? Okay, so the blue points are my simulations. The red and black points are white dwarfs that have metal lines only. The red ones are metal lines and dusty disks. And you have sort of my simulations explaining sort of the weakest accretion rates over time. So this is temperature of the white dwarf, which is sort of a proxy of evolutionary timescale. White dwarfs go from being hotter to colder with time as they cool down. And this is the mass accretion rate. So if you just took sort of an average of my models and you kicked it up by a factor of 10 or 100, or more, I can't remember now, let's say a few hundred, you would roughly match the highest accretion rates that we actually observe. So maybe we have solar systems that have a lot more rocks than we do. Maybe that's one explanation. Now, I worked with a summer intern for a while, and instead of having a small number of asteroids, we put as many asteroids as are actually observed in our solar system and tried again. And when you put a lot more, you get a lot higher accretion rates. So now it's more like we need only like 10 or 20 times what our own solar system seems to have in terms of a reservoir of tidally disrupting planets. But this is sort of like a proof of concept. We can get asteroids that start out very far with a resonance to a big planet, Jupiter or Saturn, and they get kicked in. And what's happening is it's because Jupiter is getting more muscly. Okay? So Jupiter, over its evolution, there used to be a ton of asteroids right here at the 2-to-1 resonance. This is the 2-to-1 resonance. But what would happen is once they got caught here, and eventually, so this is semi-major axis of orbit for the asteroid versus eccentricity. So they would random walk in this region and then eventually get so high in eccentricity, they escape. They either interact with Earth, they get kicked out, whatever it is. They go into the sun. But when the sun loses its mass, suddenly Jupiter is much stronger. And so everything that was on the edge here is now trapped in the resonance and starts moving around until it gets to the white dwarf and causes a dust disk and causes dust. And we can even probe, with these simulations, the distribution of how much material gets and how close it gets. So if you remember, we were seeing dust rings that were sort of in this region here, right? And so what you would expect is if something came into 60 white dwarf radii, it would shred up here, and then all the dust would sort of drain in that way. So the outer extent is a rough measure of where the asteroid maybe came in. And what this is saying is that you expect more things right at the edge of the tidal disruption radius than really deep into close to the white dwarf. So that's interesting. It also means there's a whole bunch more stuff just outside that's hanging around, waiting for I don't know what. But there's a whole bunch of stuff that doesn't get tidally disrupted that's just hanging around. It might collide. If the white dwarf is particularly hot, the stuff out here will evaporate stuff off. Keep that in mind. You've got number 8 or 9. I don't even know. Okay. Anyway, so now we can do the same calculation where we compare to a larger sample of observed white dwarfs with different accretion rates and the simulations. And now, so the solar system looks a little wimpy still, but this is sort of like your most conservative estimate of how much mass you would get accreting onto a white dwarf. But we still measure sort of the bottom fraction. But we're only like a factor of 10 or so. And at least at early times for our solar system, we can even match the highest accretion rates that are observed. But our solar system will eventually weaken pretty quickly. You run out of stuff. And it slowly falls to very low accretion rates over time. And so then these are the times after the star dies, as mapped to the temperature of the white dwarf. So we still see quite a bit of accretion in nature that we don't expect to see from our own solar system planetary architecture. So we need to investigate different planetary architectures to sort of get a hint at what maybe is causing the higher accretion rates that we actually observe. Okay, I'm going to skip that. Not very interesting. But I will tell you about a mystery. So I mentioned that Kepler had discovered many, many planets. Well, it also found something extremely weird around a white dwarf. A piddling, faint little white dwarf that everyone had ignored for many years. And someone, during K2, so remember Kepler had a main mission, its reaction wheels failed, and now it has this new mission called K2, which is doing great stuff because now it's looking at wider swaths of the sky. And they looked at this one white dwarf, and someone noticed that the darn thing kept dipping at a period of about 4.5 hours. And then when you add everything up, you see these strange dips that are pretty small. Now remember, white dwarfs are about the size of the Earth. So any dips are from small things, smaller than the Earth. So these dips all look strange. There's no way to put it. It doesn't look like a planetary transit because the dips are not regular like a transit. They're all over the place. They're kind of strange. We think we're actually seeing disintegrating asteroids in real time. Because what's happening is we're seeing these dips that are either very sharp or sort of asymmetric. And so we're seeing bits that are sort of like a comet tail, right? So we get these asymmetric profiles from the tail crossing in front of the white dwarf. And it's happening over and over again. So there's like a collection of bits going around and around. We don't really understand this yet. Literally tomorrow I am jumping on a train. I'm going to New Haven. I'm going to be observing on the Keck telescope on this object all night long. I'm just going to sit on it and see if it does something weird because it keeps changing. These dips don't stay regular. They change in depth. They shift around in time. This is like a paper that came out a couple weeks ago. I didn't even put the reference. Sorry. Apologize for that. But they noticed, okay, this is a weird plot. They call it a waterfall plot. What's happening is these are all the observations they took of the star. And anytime you see a blue feature, these were a series of dips. And they were able to match up those dips from night to night. Right? They just sat on this thing over and over and over again. They noticed that some of the dips were sort of drifting in time. So what they interpret is happening is you have a main asteroid or something, Ceres, let's say, and there are chunks of it popping off and then swirling closer and closer to the white dwarf. That's what they're interpreting these dips and the drifts and the dip times as. And when you do that, you can actually constrain the mass of the planet, or planetesimal, from how fast things are drifting. I was not aware of this, but they claim this is true. So if they got that right, they think that this planetesimal that is breaking off these chunks is about 1/10 of the mass of Ceres. So Ceres is one of the largest asteroids in our asteroid belt. So something about 1/10 the size of Ceres is not crazy for our solar system. It would not be crazy for another solar system as well. So this is starting to fill in a picture. This is sort of like the best example of a dusty white dwarf because not only do we have these dips, so we're seeing the disintegration in real time, there's an infrared excess. So we can go with James Webb Space Telescope when it launches, and we can look at the spectrum of the dust and understand something about what the dust is made of. We can see the bits sloughing off. We can maybe take spectra of the bits sloughing off and get the dust composition that way. And then when we take spectra of the white dwarf itself, it has tons of metal lines. So we can get the composition of the dust in the white dwarf. We get every step of this process with these observations. It's a really unique system, and it's very exciting. So, yay. Now, if we can see asteroids, we can see a big Earth-like planet, no trouble. An Earth-like planet will make significant changes to the brightness of a white dwarf if it goes in front of it. So this was thought of a couple of years ago. Some people have some really crazy ideas about how you could maybe even see atmospheres around these planets, even like industrial waste from civilizations, stuff like that. But I am interested in saying, can we find habitable planets around white dwarfs? Because white dwarfs evolve very slowly. They don't flare. They don't do much of anything. They're about as common as G-stars in our local galaxy. So if they host planets, which these dusty white dwarfs seem to suggest they host planets in some way, maybe these are also places to look for habitable planets. You have to get very close to a white dwarf to be habitable. So you have to somehow, okay, if you look at this, so that's good from an observational standpoint because you don't have to look at any particular object for very long to see if it has a planet because it has a nice big signal and a short period. Great. Problem is it has a short period, which means that you somehow have to get a planet that would have been destroyed during the star's death, somehow getting very close. So we see that asteroids do it. It's a little bit harder for planets. So there's no reason to expect that there are a lot of planets close to white dwarfs, but it's so easy to look, we might as well. And we only have to look at a few thousand white dwarfs to put any kind of interesting constraints on the frequency of habitable planets around white dwarfs. So, and one of the nice things is if you have a planet with an atmosphere, that signal is very, very small for main sequence stars because the transit signal itself is very small. With a white dwarf, you don't have that problem. So if there's a planet around a white dwarf, and if it has an atmosphere, it will be easily accessible in our lifetimes compared to the Earth-like planets around main sequence stars or like Earth-like or Sun-like stars. That would be very hard to do. And especially if we look in the ultraviolet, there are these large, comparatively to the visible, signatures of, say, oxygen or ozone. So I work on an ultraviolet instrument. I used to work on the COST-STIS team, and now it's the COST team. But anyway, COST has this really nice ability that any spectrum it takes in the ultraviolet can also be turned into a light curve because the detector records the time and location of every photon that hits the detector. And so any spectrum that's ever been taken by the COST instrument over the last 5 or 6 years is also a UV light curve for free. So I have a friend here at the Institute that developed software to turn every COST spectrum, whether people wanted it to or not, into a light curve. And so I asked him, can you give me all the white dwarfs, please? And there were about 100. And then I asked my high school intern, Phoebe Sandhouse. She's now a freshman at UMBC. So keep an eye out for her. I think she has a bright future because she taught herself how to program a computer, how to do research, and she found out that within our white dwarfs, some of them had been observed so many times that you actually could have seen, for a range of periods, things as small as Pluto or maybe things even as small as Ceres. That's how sensitive COS is when you have a lot of light and you're talking about a white dwarf where the signals are large. So Phoebe did this. We have a paper that is accepted by the Astrophysical Journal. It will be out soon. But basically she discovered that if you wanted to, if you found a transiting planet around a white dwarf, you could follow it up with Hubble and get exquisite precision, especially if it was an Earth-like planet, down to the levels that you would probably need to look for an atmosphere. So let's hope COS doesn't die before we find an interesting transiting planet. So James Webb will be very useful too. You can look at planets around white dwarfs in the infrared just as easily as you can in the visible or in the ultraviolet. There's a mission called TESS, the Transiting Exoplanet Survey Satellite. It's going to look all across the sky for transiting objects. So it will look at a few thousand white dwarfs for free. And so we will be able to maybe, hopefully, answer the question of whether there are habitable planets around white dwarfs. And if there are, if you find a lot of them, then they may be the most common type of habitable planet in the universe. So we have, M dwarfs as a good candidate for habitable planets because we've actually found some interesting planets in close orbits. We have Earth-like planets around Sun-like stars. Those are also very interesting because we have one habitable planet that we know of for sure, us. And then a whole bunch of other candidates that might be interesting. And then after them, white dwarfs are actually the next most common type of star. So if we can prove that these stars have planets, just like all the other stars we seem to find that have planets, well then we'll be in business. We'll have 3 different types of stars to understand planet formation about. And even if we don't find any planets around white dwarfs, that's okay because we certainly see the fingerprints of rocky planets around white dwarfs, and we can get a really good idea of how rocky planets form in the universe. So, dusty white dwarfs. They have tiny little disks. They are caused by asteroids that shred up. The dust turns into a disk. It eventually accretes onto the white dwarf, and you get a fingerprint of the dust's composition, right? Elements and relative abundances. And then we are actually seeing this disintegration in real time around dead stars. And we think there might be a lot of planets around these white dwarfs that are really interesting to follow up on. I should also mention that James Webb will actually be sensitive to find Jupiter-like planets at large separations from their white dwarfs, presumably the perturbers that cause all these dusty conundrums. So with that, I'm just going to advertise a citizen science project that I'm part of called Disk Detective. So if you like dust, or if I have suddenly convinced you that dust is the most amazing thing in the universe, you can look for more dusty stars with Disk Detective. It's through the Zooniverse website, and that's a fun thing to check out. You'll help us find dusty stars yourself. And with that, I will be happy to take questions. Thank you.